Hey, this is Mr. Herzon, honors biology teacher at Thomas Wooten High School. And today, we're taping this segment today on Tuesday, June the 1st, 2021. In today's episode, we are checking for understanding the Hardy Weinberg problems that were assigned last week. Before we start, I do want to go over the Hardy Weinberg equilibrium and what that really means or what it translates to. If you look back here, if you look up here, all right, it really means that in a sexually reproducing species, their variations remain constant from generation to generation under certain conditions. Okay. And all five of these conditions must be met. Okay. It's kind of like, on Fantasy Island, so to speak, because really, um, you don't have so much control over living organisms like cicadas. Okay. So let's keep cicadas in mind. All right. Um, no evolution would be taking place with the cicadas. Um, um, for the reason is that Hardy Weinberg um, requires random mating, meaning male cicadas can't seek out and pick out the female cicadas. Actually, it's the other way around. Since the males are the ones that make all the noise, they're trying to attract the females. So it's the females that make the selection process. Okay. Um, you need a large population size. I think if you look at the entire Rockville or Montgomery County or the state of Maryland, you got a good population size there. No problems. But there can't be any mutations. Most of them, of the cicadas, have a red eye, but there's a lot of other variants out there. One particular that people like to look for are the blue-eyed cicadas, and they, in addition to the blue eyes, they part of their wings are kind of like um, a southern blue color. Okay, really, really light blue. All right. There can't be any migration. Okay, there's none of them that can drift to a different geographical location. Um, there, uh, um, there are none coming in to the population, and then, yeah, right. No natural selection. What is the lifespan of a recently emerging cicada? There's even domesticated animals like cats and dogs run after these guys and gobble them up. I mean, they're such a delicious protein snack for them. So all these conditions have to be met in order for equilibrium to take place, and that stands to figure. Now, if the frequencies are changed throughout a number of generations, we would say evolution does exist, okay, or is in the process of evolution. All right. So, looking at question number one, all right, identify the Hardy Weinberg equation that represents genotypic frequencies in a population. Okay, so number one, that would be p squared plus 2pq plus q squared equals 1. Okay, p is the dominant allele. Okay, and q is the recessive allele. Now, sexually reproducing organisms are made up of a combination of alleles, either two dominant or two recessive alleles, or a hybrid, okay? One of the dominant and one of the recessive allele, okay? So if we look here, all right, at p squared, this refers to the genotype of homozygous dominant, okay? If we look at 2pq, these are the heterozygous, all right, genotypes. And then q square is homozygous recessive genotypes, okay? Question number 2 is, what is the equation for the allele frequencies, all right? And that is to say, if you count up all the dominant alleles and count up and add those to all of the recessive alleles, that's going to equal to 100% of your population, or one, your entire population. So one refers to the entire population. Okay, all right. So if we set up a Reginald Punnett square, all right, okay, and we cross two heterozygotes, okay, so the possible gametes could either be a gamete with the P allele or the recess of the Q allele. And the same thing on this side. And it really doesn't matter. I'm going to just say that the male gametes, the sperm cells, are on the top, and the female gametes, the eggs, are on the side here. Okay, so if this sperm fertilizes this egg, our zygote is homozygous dominant. Okay, and I'm going to circle this in blue because homozygous dominant, remember, that is this variable in this equation. Isn't that neat? Okay. Now, if this sperm fertilizes this egg or this sperm fertilizes this egg, we have the heterozygous. Okay. And I'll use the color black. Okay, so this one here and this one here added together, that's what gives you the heterozygous right here. Okay, and then, oops, if this sperm fertilizes this egg, that's the homozygous recessive. Make that in purple. Okay, so now you can see how, the frequencies of the alleles, all right, can be used to help find genotypic frequencies. All you would have to do is square the the value, the frequency for the dominant allele, and you would get this genotypic frequency. Okay, and likely, if you found the genotypic frequency for a population, you can find out what the allele frequency is. Okay, and that's what all these problems, genetic problems, are doing for us. Okay. Now, we'll look at the problems next. Okay. All right. The next set of problems refer to on this gene pool. Okay. And one thing that I wanted to show you was how you can quickly amass the totals in the alleles. Okay. So we have a lot of alleles. There's actually 50 of them. Actually, it would be helpful if I had this to dry it out. Okay, perfect. All right. So one thing that I do on the worksheet is I'm forming like a little table. Okay, and in this there's all of these alleles that I have written out. Okay, and there's a lot more here, and there's some down here. Okay, and so what I have done is make a chart, actually a little bit more. Okay, this is going to be my total here. So I got total and the number of dominant alleles, and then we need a column for the number of recessive alleles. Okay, so up here on the top, you can see on the top row, there are 25 total alleles. 5 of them are dominant, 20 are recessive. And in the second row, there's 25, but only 3 of them are dominant, while there are 22. Okay? This way, you can calculate the grand total. All right? 8 dominant total alleles, and then 42 recessive alleles. Okay? So in question number 8, we are trying to find out the dominant allele frequency. So the dominant allele frequency, that's going to be equal to, there are 8 total divided by the grand total number of alleles, which is 50. And that's going to be equal to 0.16. Okay. All right. Question 9. Oops. Question 9. All right. Here's where we're finding the recessive allele frequency. All right. And we have 42 recessive alleles out of 50, and that's going to be equal to 0.84. Now, maybe you have found this by subtracting 0.16 from 1. And you remember that in one of the Hardy Weinberg equations for allele frequency, P plus Q equals 1. Okay, so here we have found out what P is. All right, and we know that if we subtract P from 1, that's what will give us the recessive or the Q allele. Okay, so if you didn't figure out this way, and but you subtracted one. I'm sorry, this from 1. That's fine. That's fine. You're good. Okay. All right. Good. All right. Now, what I want to do is set up the Punnett square um, for question 10 and 11. Okay. All right. So we're going to cross two heterozygotes. All right. The frequency of our dominant allele here is 0.16. And for the recessive allele is going to be 0.84. Okay. And the same thing over here. All right. So F homozygous dominant is found by squaring 0.16. And when you do that calculation, that equals 0.0256. Okay. Now, a lot of students will ask, well, when should we round? Or should we round up? Should we round down? Okay. I don't like rounding. Okay. The maximum I will go is usually to the 1/1000th of a place. All right. So that's like 3 decimal points. Okay. But here you know, um, this is very close to the midpoint um, of, of having, I don't want to round up, okay, unless, it's not 0.26 yet, okay, all right. You could round up to 0.26, but remember, when you round up or round down, that is going to change numbers when you use these genotypic frequencies to find out how many individuals that there are. So if you round here, that's going to affect your population totals. Okay, that's why I don't like rounding. Okay, all right. For the homozygous recessive, we're squaring 0.84, and that is going to equal 0.7056. Okay, all right. And then these are the heterozygotes. Remember, we have 2 of these. So this is going to be 0.16 times 0.84. And the same thing down here. Okay. And that is going to equal 0.1344. Okay. All right. So there's our heterozygotes. So now we can look at question number 12. Okay. This is 10 and 11. Okay. Now question number 12, calculate the genotypic frequency for the polydactyly trait. Okay. Hint, remember that the trait is autosomal dominant. Okay. So polydactyly is an autosomal dominant trait. Okay. Is that okay if I switch to blue? because this is really exciting stuff. I really got to highlight it a lot. Okay, so what this means, if you are homozygous dominant or heterozygous, you express the polydactyly trait. Okay, so now you have to include both of these. Okay, well, this means we already can we find out what um, f squared is? Yeah, we can. We got it right over here. Okay, so I have that number. Okay, and I also need both heterozygotes. Okay, that means I'm going to include this value here, and I have to include this value here. Okay, so this is going to be equal to 2 times 0.0256 plus 2 times 0.1344. And when you put that into the calculator, all right, that means the genotypic frequency for the polydactyl trait is 0.2944. Okay. Now maybe you moved it down to, or you just kept it as 0.29. That's okay. All right. But remember, all right, when you round down, when you're dealing with populations, that's going to alter the number a little bit. Okay. To a lot, depending upon how much you round. Okay. So now we want to know, move the camera here just a little bit. Actually, yeah, it's fine. Okay. So let's actually come on up here for number 13. All right. Okay. So here we want to know the ones that are phenotypically normal. Meaning that they don't have, they are the trait polydactyly. They don't have extra fingers or extra toes. Okay. Maybe there's an evolutionary advantage of having more fingers and toes. You know, if you're an Oompa Loompa and working at the chocolate factory, you can mix the chocolate a lot faster with more fingers. Okay. Or you're faster at wrapping candy. Okay. In the wrapper or presents. Okay. All right. All the neat stuff. I'm getting hungry. All right. So the ones that are phenotypically normal are going to be which genotype? Yep, this one right over here. Okay. F, um, both the homozygous recessive. All right. And that's going to be equal to um, 0.7056. Okay. Now remember, how many Oompa Loompas are there that are normal? We have to multiply this by the total population, which is 1,772 Oompa Loompas times this frequency. Okay, this will give us, all right, the population that is normal. Okay, so how many Oompa Loompas are normal? That comes out to 1,205.3. Okay, now maybe you might have, oh, I'm sorry, a little dyslexic here. um, let's change that. Okay, that comes to 1,200. Yes, of course. 1,250.3. Okay. Now, your answer, depending upon how you rounded in doing these calculations over here, all right, could have an effect on your total population. All right. So the less rounding, all right, the more precise your value is. Now, you won't be taken off for having a different number than this, okay, within an accepted range. All right. I usually factor all that in for students, okay, because it's kind of hard to get everyone on the same page from rounding because they come from different math classes that have teachers that may have an exception of saying, oh, well, you round this up to 0.2 and you round this down to 0.8, okay? So that would have a dramatic effect on the population numbers, okay? And then lastly, for number 14, okay, do you have any carriers? All right. Well, remember the term carriers refers to a genotype, not a phenotype. So the carriers are designated as the ones that are heterozygous. Okay. But remember, this allele is dominant. Okay. So basically, there are no carriers. Okay. For the simple purpose, so um, if you are homozygous dominant or heterozygous, you express the polydactyly trait. Right? Right. All right. We're in the home stretch. It should only take another minute or so. One thing that is good to note that when you're doing these problems, okay, the probably the hardest part is actually figuring out where to start. Okay. And for these next few questions, that's what I'm really going to hone in on. Okay. Where to start. Okay. So we got a Punnett square. Actually, let me dry this off just a little bit more. You know, um, Sometimes you may be presented uh, um, with population numbers, and from the population numbers, okay, you can figure out the genotypes, and from the genotypes, you can figure out what the allele frequencies are. Okay, sometimes you're given the number of alleles, dominant ones and recessive ones. So if it really depends upon where in the Punnett square you are starting, not where in, where in in terms of a Punnett square, all right, the information that you're given in the stimulus, all right, is it referring to um, alleles, which would be on the outside, okay, or is the information referring to genotypes? Okay, if you are being given letters like G, 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 little g, okay, those are individual alleles. You can actually find out the allele frequencies for the dominant and then the recessive, okay, like this, all right. um, for the dominant allele is equal to 2 divided by 4, which is equal to 0.5. And the same thing for the recessive allele, all right, is equal to 0.5. So the information that you're given here is actually telling you what P or and Q is, but it's really G and little g, the dominant and the recessive alleles. So you know you're starting on the outside of the Punnett square. But what if you're given population numbers? Okay. You have, let's say, 10 individuals of your population, all right, and two of them have the disease which is autosomal recessive. Okay. So if you're being given that value, all right, in which um, there are two people out of 10, okay, all right, you are looking at the genotypic frequency, which 2 divided by 10 is equal to 0.2. Okay, all right. So you know this is for g squared is equal to 0.2. Now you can find out what the recessive allele is by taking the square root of 0.2. Okay? So once that you know what the recessive allele, you can subtract it from 1 to find your dominant allele. And from that, you can fill in the rest of the Punnett square. Okay? So in this type, if you're actually given the number of people, you're sitting on the inside of the Punnett square going to the outside. Okay? That's an innie-outie. All right? If you come up with mnemonic devices that are a lot of fun or really kind of strange, you'll remember it better. Okay? All right, let's tackle the rest in high speed form. All right? Oh, not that kind of speed. All right. Calculate the allele frequency for green hair color. Okay? So the story goes that um, Also evident in the village of Wonkaville is the observed green hair is dominant over cyan hair. Of the 1,772 Oompa Loompas, 392 have cyan hair, while the rest have the green hair. If you notice, I went right away for the genotype for homozygous recessive. Okay, that we can find out right away. So that what that means is that we really need to skip a question in order to answer the question. Because number 15 is asking for the allele frequency for green. And that's going to be hard to figure out because the genotypes for green are homozygous dominant or actually, and heterozygous. The problem is that you don't know from the ones that have green hair, are they homozygous dominant or homozygous recessive? So that requires you to find out what 16 is first. Okay, allele frequency for cyan. Okay, hair. This GG or G squared, homozygous recessive. Okay, so we know this. Okay, because of we have 392 Oompa Loompas that have cyan hair. Okay, divided by the total population. Okay, and that is going to be equal to G squared, which is 0.22. Okay, all right, so G, finding out what G is equal to the square root of 0.22, and that is equal to 0.47. Okay, now here, G plus the dominant allele plus the recessive allele equals the entire population. So therefore, if we G, the dominant allele, is going to be 1 minus 0.47, and that equals to 0.53. Okay, so here is the dominant and the recessive allele values. Okay, all right. And then finally, we can figure out the heterozygote frequencies. Sometimes it's good, if I blow, if I'm like really desperate for space. All right, let me turn the camera here a little bit. All right, I'm over time by 10 minutes. Okay, and not too bad. Okay, 40 minutes. All right. Remember, an entire period of 60 minutes, so I'm really doing fine. So now we're on to question number 17. Okay, and in 17, we want to know the genotypic frequency for heterozygous individuals. Okay, so genotypic frequency for heterozygotes. I'm just going to abbreviate that as HZ. All right, so the heterozygotes are equal to, I'm sorry, looking at the Hardy Weinberg equation, okay, it's going to be 2 times the heterozygotes in the Punnett square, this value right here. Okay, we already know what these alleles, the values for them, 0.53 times 0.47. Okay, when we do this, the heterozygote frequency is 0.498, and you can leave it this way, or, this is very close to, approximately, that's what this symbol means, 0.5. Okay, again, be careful, about how much you round. Even this will lead you to be off by 1 or 2 people for um, uh, the next problem. Okay, so number 18, this time you want the genotypic frequency for homozygous dominant. Okay, all right, so homozygous dominant is equal to, all right, or or G squared, which is equal to 0.53 squared. Okay, and that comes out to 0.2809, or which is approximately 0.281. Okay. Now, question number 19. Our total population was stated in the opening paragraph. All right. And that is 1,772 people. Okay. 20. Okay. How many Oompa Loompas in your population are heterozygote? Okay. So remember about rounding. Okay. I'm going to show you a difference here. So recall that heterozygotes is equal to 2G, 2 times the dominant and the recessive allele, multiplied by the entire population. Okay? So now I'm going to substitute 2 times 0.498. I'm sorry. I'm sorry. The whole value, this is equal to 0.498 times 1,772, and that comes out to 882.456. Okay? Now you really can say, well, I'll leave it as 882.5. Okay? I'd feel comfortable about doing that. Now, if your value here was 0.5, all right, when you multiply this, your final number could be like as up to 883. All right. Hey Siri, what is 0.5 times 1,772? 8,000. Oh, I'm sorry. It didn't do the point 0.5. um, actually, um, yeah, if this was point 0.5, you would get 886. Okay? That's just from rounding from 0.498 to point 0.5. That's all you did. Well, now look how the difference of your population is. Okay? And that's simply the reason why like this is an overestimate. Not by a lot. I mean, it's okay for us in honors biology, okay? But really, when you get into population statistics, all right, for genotypic and allele frequencies for cicadas, or if we're talking about COVID 19, and really in the Department of Interior, they're actually going to be using Hardy Weinberg to actually predict how many people would be, for example, totally immune to COVID 19. You know, the two spikes on the surface of the virus, um, and how many people would be susceptible. Okay, um, they would make these predictions, and this is something that the Johns Hopkins University was doing, in addition to the CDC and the World Health Organization. Okay. Um, there's a lot of values that go into um, calculating all of this. All right. It's a lot of logarithmic types of functions, but this can give you like an idea, all right, of how many individuals may be susceptible um, to a resurgent in the virus, okay? Or if the next 17 years, are we going to see different allele frequencies for our cicadas, okay? Still looking for a purple dye cicada. So if you come across one, all right, please let me know, or you can put it in an envelope and put it in my mailbox here at Wooten High School, okay? This is Mr. Herzon, wishing all of you a very great day, and we'll see you next time. Bye bye.